All right. Welcome everyone in the room and online. So it's very nice to have Adnan Bashir visiting us from University of Huelva and the University of Michoacan. I wonder which one you spend more of your time in. Those are very far apart places. But yeah, it's very nice that you could be here. So Adnan's also one of the people in Australia down for the confinement conference, which happened in Cairns last week. So we're going to have another nice talk about QCD. So I'll leave it in your hands. Thank you.
Okay. Thank you very much for having me here. Although I think what I do not exactly overlaps with what some of you do. I had a chance to go to Adelaide, but there were so many people going to Adelaide after the conference that I decided to come here to Sydney, look around and have the chance to talk to you on some of the things that I do. So I was asked to make a good part of this talk a bit introductory so that people can know what it is about and give less details of the quantitative mathematical work. That's what I have tried to do. So I think my first few slides will contain most of the things that you already know. But as we know that Enrico Fermi had once said, at least people say that he's the one who said it, that one should never underestimate the joy we derive from hearing something that we already know. So that should be good enough. So he asked me where I spend most of my time. I actually don't know myself at the moment. I've spent a lot of time in Mexico. I haven't been there now for a couple of years. I spent a year in Jefferson lab in USA, and more recently I'm still on leave from Mexico, and I'm working in Huelva, Spain, in the region of Andalusia near Sevilla. If you have been there. Neither I know where I've been in the last few years, nor I know where I will be in the next few years. I might stay on in Spain, and I might go back to Mexico. Right now, I'm in the superposition of both states. So here we go. I work mostly on QCD, physics of protons and neutrons and pions and kaons. They are made of quarks and gluons. So we start from the equations of motions of these particles, quarks and gluons, and try to understand the structure of hadrons, what they make part of. Okay? So I'll try to make a useful connection with what some of us already know. I think most of us have studied what hydrogen atom is when we study classical mechanics or even quantum mechanics. Especially in quantum mechanics, this is one of the bound states, one of the physical bound states that we have the first encounter with when we study Schrödinger equation. But we all know that we understood a little bit more about hydrogen atom starting from the experiments of Rutherford in 1910, and then his communication with his classmate, which was Niels Bohr, of his results, who was a theoretical physicist. And from 1910 to about 1980, Bohr, Rutherford, and many others understood much better the structure of the hydrogen atom, their energy levels, the mass spectrum, and the transitions. So that knowledge was quite good. It was supplemented later on by the work of Schrödinger and others who started quantum mechanics in 1924 and 1925. So by that time, everything was looking quite good. But then experimental programs became better. We knew a lot more about the transition that took place between different energy levels of the hydrogen atom. And eventually in 1947, there was a conference in Shelter Island on fundamentals of quantum mechanics, in which Lamb presented his work that he had done with his student Rutherford. It's not the same Rutherford, it's a different one. There he presented the difference of two spectral lines. He showed us that despite the fact that Schrödinger equation didn't allow it, 2s half level and 2p half level of the hydrogen atom did not have exactly the same energy. Their energy level difference was very small, about 5 orders of magnitude smaller than the usual energy levels that we find in the hydrogen atom. But they were able to measure the difference between the spectral line that made the transition to that energy level. So that was a very interesting conferences. Lots of big names in theoretical physics had gone there. Dyson was there, Feynman was there, Schwinger was there, and they had no idea how to explain that. Theory was completely failing by that time to understand that. And that actually made Dyson say that if you don't understand the hydrogen atom in QED, you don't really understand anything, because it's a two-particle bound state. If you can't explain it from QED, what really we can do? So understanding this two-body system and the transitions, the energy transition that took place inside that hydrogen atom led us to the deepest understanding of quantum electrodynamics. Okay, we understood it gave birth to renormalization. And once we understood renormalization, we could calculate many radiative transition, radiative corrections, not just to the Lamb shift, but also to the Muon G-2, about which I will talk a little bit. And therefore, we realized the importance of that. Renormalized quantum electrodynamics is one of the most beautiful and profound things we understand in physics, and that understand stem from this two-particle bound state. So I'm making a case for the two-particle bound states, and in strongly interacting systems, the simplest two-body bound state we think we have pion and kaon. So the pion is made of up and down quarks. There are three types of pions, and kaon is made of up quark and the strange quark. Strange quark is slightly heavier than the up and down quarks. And these are, of course, the simplest two-body bound states in QCD. And if we do not understand these things, we don't really understand QCD. And as we stand today, we don't really understand them. So we don't really understand QCD to as much detail as we would ideally like to understand. But in fact, it's a much bigger challenge for QCD. QCD has been known for about 50 years, more than 50 years. And it is a simple system. We still find it a bit hard to understand. And I'll talk along the way what are the difficulties. So these are strange particles, these pions and kaons. These are not only the bound states of quark and an antiquark, but they are also what are called the Nabu-Goldstone bosons associated with dynamical chiral symmetry breaking. There is a global symmetry which is broken, and the number of broken generators correspond to the number of bosons which should exist, and those are the pions. Most of us have seen this. This is the Nernst theorem. So they have two different kinds of structures. So talking about this two-particle bound state that I will be talking about, pion and kaons, we know about them for a long time. In fact, when neutron and proton were discovered, neutron finally in 1932, that was the same year that Heisenberg gave the idea of isospin, symmetry between neutron and proton. Three of the most important works were done in 1932. Discovery of positron also took place in 1932. And that was, interestingly, the only year when no Nobel Prize was given, saying that nothing important was available to be given the Nobel Prize. But anyway, that happened. So after that, in 1934, Yukawa predicted the existence of a meson that should be exchanged between proton and neutron, just as a photon is exchanged between electrons and positrons. So he gave the idea, and in 1934, he got the Nobel Prize in 1949, just 2 years after pion was discovered. And pion was discovered by Cecil Powell in 1947 in the experiments of cosmic rays. And he himself started an experimental method to do so, for which he himself got a Nobel Prize in 1950. So the story of pions actually began in 1934. And in my personal opinion, one of the very important steps took place when Nabu wrote a couple of beautiful articles in 1960. He got a Nobel Prize later on for for his work in 2008, not long ago. That was a time when proton and neutrons were known, but the idea of quarks was still not given by Gell-Mann, which came a few years later. So if you read the article, if you read the abstract of the article, Nabu was saying that he doesn't know why exactly proton has such a large mass, but probably it is due to some elementary field which should have chiral symmetry, which should be broken, and that breaking of chiral symmetry should give proton such a big mass. So he knew about what was happening. He knew it should be, well, some quark. He didn't know that it was there. But anyway, we all know that NAMBO could look ahead in time. I don't know if everybody has heard some story about NAMBO. There was so he gave the idea of this even before the discovery of quarks. Now we know quarks exist. They more or less obey chiral symmetry, and the breaking of chiral symmetry gives a lot of mass to the protons and neutrons and to the pion itself. Then there was a famous scientist, so famous that I don't remember his name, but he wanted to do his PhD, and he decided that he should work with NAMBO, because everybody said that NAMBO could look ahead 10 years. He was always 10 years ahead of other physicists. So he said he went to NAMBO and asked for a problem, and NAMBO gave him a problem to work on. He came home, looked at the problem. He had no idea what NAMBO was talking about. And he said he tried to understand. By the time he understood it, 10 years had passed. So, so it didn't work for him so much. Anyway, coming back. So now we know existence of pion and kaons when they came into, when we knew about it, why we knew about it. And the second thing is, after knowing them, do they have an internal structure or not? So we knew about protons and neutrons and pions and kaons for some time. There were lots of particles and all were considered to be point particles. But then eventually, Hofstadter, he started works in 1950, started talking about what happens if you have the Rutherford formula, Rutherford scattering formula, but what if the particle is not really a point particle, but there is a little bit of charge distribution, how much things will change? And the Fourier transform of that charge distribution was called form factors. So he started started studying the form factors of lots of nuclei. Heavier nuclei, lighter nuclei, carbon, oxygen, helium, hydrogen, and try to map out the form factors and charge distribution and charge radii of these particles. So he started working in 1950, did a lot of work for 10 years or so, and I think that he got the Nobel Prize in 1961 for his studies. So his studies were based upon elastic scattering of electrons, scattering of nuclei, and you don't have to really break it, but still it gives the information of the charge distribution inside these particles. So that was the first hint we were getting of the internal structure of this in terms of how the electromagnetic charge was distributed. So these form factors and this charge distribution is the Fourier transform of that in the position space. Then in 1960s, there were experiments which were called deep and elastic scattering experiments. People were trying to hit the protons and neutrons with highest energy to try to break them apart and see what was coming out. They were not so different from the Rutherford scattering experiments. He was just using helium and gold. He was only using 5 MeV energies for the helium particles. And if I'm not wrong, these 1960 experiments were using electrons of about 20 GeV because you had to go much smaller in the resolution scale of the atom to see inside protons and neutrons. That led to the discovery of quarks. But in those deep elastic scatterings in which an electron comes and really breaks apart the system into many things, there was another interesting idea came, and that was given by Feynman beginning in his famous article of 1969. He started talking about what is called the Parton distribution. It means how much momentum fraction a parton, a quark, or a gluon has of the total system in the longitudinal direction. And that was because the scattering was so hard that everything was going in one single direction, basically, after the proton was. So even if you have read this article, if you've not read, this is also one of the most beautiful articles I've ever read. No equation in the whole thing. Abstract is one line. I introduced the idea of Parton distribution. That's it. And no equation, and he explains why he has to do it, the time scales involved in different parts of it. There was a hard scattering part, there's a soft scattering part. And now you go at the experiments, so many experiments in the world, they're measuring the Parton distribution. People are calculating, and still there is a. So I think my 1 hour is finished. And I don't know how much, 10 minutes, 15 minutes. I think I'm going very slow. I'll probably never go to what I have to talk about, but probably you'll not be interested in that part anyway. So, so then in 1990s till now, about a quarter of a century from now, backwards, people started discussing about what are called the generalized Barton distribution. Can you really make a three-dimensional image of these hadrons, protons, neutrons, pions, and kaons? And then you have to introduce another momentum fraction, which is called the off-diagonal momentum fraction these partons have in the transverse directions. So your internal structure can be a function of x, function of xc, and also a function of q squared that this electron gives to the system, and then it gets distributed in different ways in the final. So you can have a photon, you can have a meson, or you can have some other things, and that is making life a bit more complicated. So your internal structure can be a function of three of these variables, either q squared or x or another variable that I will come to a bit later on. So this is, first it was about what are pion and kaons. Secondly, how do we study the internal structure of these hadrons? And now, if we learn the structure of particles, which is very important these days, everybody says we want to build a three-dimensional picture of these hadrons. What do we learn from that? Is it just knowing the structure enough, or is it going to lead us somewhere? So the idea is that to understand how this structure is formed because of the interaction which takes place inside it. So that tells us that we have to understand QCD, because it's the dynamics of quarks and gluons which gives the structure to these particles. What is also interesting, and we sometimes somehow do not appreciate it, that we are lucky that quarks also have electromagnetic charge. So although the structure of these pions and kaons is given by the strong interaction, many times we measure that structure through electromagnetic probes. So we know where they are, how much momentum they have, although where they are and how much momentum they have is due to QCD, but we can see and look at it through electromagnetic probes. So QCD, we all know, for example, many of us have seen the Lagrangian of QCD. It doesn't look very much different from quantum electrodynamics. The only thing is, instead of having U1 local gauge invariance, it has SU3 local gauge invariance. And that means that there are three quarks in the fundamental representation of three different colors. Instead of one photon, we have 8 gluons. And instead of photons not interacting with each other, gluons also have self-interaction. There are triple gluon interactions and 4 gluon interactions. The structure of QCD is basically very much similar to QED. The only thing is that it has strong interactions for various reasons. One of them is simply phenomenological. And that strong interaction leads to phenomena that no other fundamental interaction has ever seen. And those are two phenomena which do not emerge directly from the Lagrangian, but from its infrared dynamics. And those are called confinement and the mass generation. And confinement was the topic of the conference that took place in Keynes last week. We know from, since about 1968 or 69, that quarks have color and color is confined. You cannot see colored particles in the detector, and we still do not understand why. So quarks and gluons do not reach detectors. Neither quarks and gluons reach detectors, nor any of their color combination has ever been seen to reach the detector. You can hit these particles as hard as you want. You can break a proton and neutron. You can produce lots of hundreds and thousands of quarks and gluons, but much before they reach the detector, they conspire among themselves to form color-neutral particles, and these are the color-neutral particles which reach the detectors. Why they're confined, we do not know, and I do not claim that I'll tell you today why they're confined. So there is another thing. How come proton and neutrons are so heavy? Those who have studied the Lagrangian of the standard model, we know that all fundamental fermions, in fact, all fundamental particles obtain their masses due to their interaction with Higgs particle. That's why people call it a quad particle. The interaction with fermions is hand put. It has the right symmetry in it, and the lightest quarks, up and down quarks, have this mass of about 3 MeVs, 4 MeVs, 5 MeVs, and that is given to it by the interaction with the Higgs field. Okay, but we know that proton and neutrons have the mass of about 1,000 MeV. So it's if you put together 3 masses just by hand, it's about 100 or 2 orders of magnitude better than that, and we do not understand. we attribute it to the dynamics of QCD as well. So much mass it is given that I think almost all the mass of the visible matter that's seen in the universe comes from the QCD dynamics, and the one that we attribute to Higgs is very, very small. So we don't understand confinement either. So there are many ways to study QCD, and a popular way to study a QCD is lattice, okay? And I don't usually do popular things, so I will not work through lattice. I would work through what I call the fundamental equations in continuum of quantum field theories, which are called Schwinger-Dyson equations. Many people also don't know, I think, what Schwinger-Dyson equations are and how do they work. So I'll give a brief introduction to that as well. So we want to understand these phenomena and how these help us understand the internal structure of pions and kaons, what we wanted to know. So origin of confinement and this mass generation might perhaps be traced back to the green functions of quarks and gluons, that is called the quark propagator, the gluon propagator, the quark-gluon vertex, interaction vertex, gluon interaction vertex, etc. Okay, so that is something which we call the mass function. It's a slightly deceptive concept, but if you don't find what is wrong, I'll not tell you what is wrong. So the mass function is like, in some qualitative way, tells us how the mass of a quark varies as a function of the momentum probe. So what happens roughly is that, when quarks are inside a pion or a kaon, when they're very close to each other, they don't see each other very much. That is what is, we know as asymptotic freedom. But when they start going away from each other and when they traverse the distances of a hadronic size of about 1 Fermi, then they become much heavier. So that is what something like it tells us, that if we have like up and down quarks that pions and kaons and protons and neutrons are made of, they are only a few MeV in the Lagrangian due to the Higgs mechanism. But when they started going away from each other, their effective mass increases. And by the time they're very far, but still inside the proton and neutron, their mass is about 300 MeV effective mass. And when you put them together, that's roughly about the mass of a proton or a neutron. So that comes from studying, so this mass generation mechanism we can understand at the level of quarks. Then why does it have? So this emergent phenomena, which is confinement, what I have not talked to you about is that confinement can also be associated with these propagators, but we still don't know exactly how. Okay, that's one of the things I study, but there are no conclusive remarks that I can give you. So these emergent phenomena of QCD, non-existence perturbation theory, are naturally linked to the strong coupling dynamics. We believe that our experimental and theoretical colleagues tell us that the coupling of strong QCD becomes large. It doesn't become infinitely large. It probably settles down and saturates at a certain value, and it's of the order of 3 or so. And that is good enough to give way to these non-perturbative phenomena. Now that's debatable and not debatable how it works, but most of us believe that. Then the third thing is that the effect of this mass generation and effect of the confinement mechanism eventually leads us to things which run with momentum. Like this mass of the quarks run as a function of momentum or the function of distance, running coupling is a function of momentum, and eventually the form factors that I'm going to talk about are a function of momentum scale. And these all momentum scales, or their momentum dependence, is quite related to each other. So I'll give a little bit more of introduction, and some of the things I will go eventually a bit faster. So if we have talked about QCD and we talked about this chiral symmetry breaking, and if I'm telling you that when the quarks are away from each other, the effective mass increases by this, is there evidence for that? Experimental evidence, and where does it lead to? So one of the first evidences that you can find is the following. Again, I'm going to talk about something that you probably already know. You see Lagrangian, and you have studied, for example, many symmetry transformations, and one of the symmetry transformation is chiral symmetry or axial symmetry. So if you imagine for the time being, which is actually not always correct, that pion, rho particle, A1 particle, all made of 2 quarks, that these are only quark-antiquark states and there is nothing else inside. So if you do this, then this is the operator which defines it, so the quark and an antiquark. This tau is because of this isospin as gamma 5 because it's of parity, it's a pseudo-scalar particle. This is scalar, so it is psi bar psi. This is rho is vector, that's why there is a gamma mu, etc. And that's an axial vector. Now, there is something called axial transformations. You don't usually show it. I didn't show it in Kaons. But this is the axial transformation at SU2 level. If you do this rotation of this fermion field, what you will find eventually, it's a little exercise you can do to psi and psi bar. And once you do it, what you find is here, that if you do a transformation of this sort here, you will see that there is an admixture of the other state which comes in. And if you rotate it to a certain angle, then you can see that this particle gets transformed into this particle and back. And this particle gets transformed into that and back. So if this symmetry, what is called the chiral symmetry, is a good symmetry, if it is conserved, then these particles should have the same mass. But they don't have the same mass. In fact, the difference of masses between these particles is about 500 MeVs. And the difference of particles among these is also about 500 MeVs. So this is about the mass that a quark is achieving in the non-particle. So there might be a connection. Now this part is very, very debatable. So I better not go so much deep into this. This proton has it's a parity plus spin half particle. The nearest opposite part parity particles is n star 1535. And if you do these kinds of rotations, you will see that this proton gets rotated into this and this gets it. So it's like a parity partner of proton. And that's also about 600 MeVs. Then there are other particles, these delta particles, and the parity partner of this is supposed to be this one, opposite parity, and it's also about 500 MeVs. So you see that, we can tend to see that there might be some effective connection between these stories. So that's what we want to study, that this chiral symmetry breaking can explain the internal structure or not the way we want to see it. So I wouldn't use the tools of lattice QCD, but I will use the tools of what are called Schwinger-Dyson equations. And many people haven't seen these equations, so I will probably try to say something about what these equations are. But of course, as any good teacher, you see the easy example in the classroom, and then you give the difficult example for you to see at home. So that's what I'll do. I'll look at Schwinger-Dyson equations in quantum electrodynamics here, and for QCD, I'll not dare do that. So this is the electron propagator. Many people know that in quantum electrodynamics, that's the Baire propagator, which is 1 over p/-m. Okay. And then, you can have virtual corrections coming. So this is an electron propagator. So there are many virtual corrections. It can emit a photon, absorb it. It can repeat it. It can do it that it can emit one, then another one, then absorb first, and then the second one. And that photon can, get transformed into electron-anti and electron-positron pairs, or they can be corrections of this time. So all this happening, and this, in terms of Feynman diagram, was looked at by Dyson in 1949. So what he observed was that these have a certain structure. All these contributions of this sort, in fact, can be squeezed, and it can be considered as a correction which takes place to this propagator. Okay, because it doesn't interfere with that photon or the vertices. So all these types of corrections can be written like a blob. It can contain everything which is happening in that. How many times it happened, it doesn't matter. And all these corrections which are happening to the photon propagator can be summed up as all the corrections which are happening here, and all these are here. Now one can say that, look, this is happening here, but this could be happening here as well. But in fact, it's topologically similar. You can turn around and basically all of this is happening in one vertex. If you do at the two vertices, you'll be double counting the diagrams. So when Dyson looked at all these things, and he wrote this equation that you can really look at it, all these things happening, and then it can get repeated. So the equation can be written like that. Okay, then because it can, you can keep expanding it like that. So then he said that if I define, it's called the self-energy of an electron because it's self-interaction, I can write this as a Baire propagator, this is the full propagator, And all these things, this is a bare propagator, a full propagator, and then there is a self-energy, and then bare propagator, self-energy, another bare propagator, another self-energy, and this series you can go on writing all this series. And then you can see that from here on, I can take this as common, and whatever is left is in fact what was here. Okay. So therefore, all this which is in the bracket is nothing more than the original series, and I can call it the full propagator, and I can write this in the simplified form. And once you do this, I multiply from right with S inverse P, and from the left with S 0 inverse P, and I can write this in a very compact form, this equation, and this looks like the gap equation. And there he says that, well, so this is not anymore perturbative because you have summed up all the diagrams, but summing up all the diagrams, it not necessarily always means that it is something non-perturbative. That's another thing that we have to be careful about. But anyway, he derived to this, all the sum of the diagrams and called it's the Dyson equation for the electron propagator. You can repeat this game for all other green function. This is the equation for the electron propagator. This is the equation for the photon propagator, and this is for the vertex itself. So you see that if there is a 2-point green function, it has a 3-point green functions in it, okay, related to it. Then there is equation for the 3-point functions, and it has 4-point functions in it. This is not a point interaction because it's a blob. It starts with an interaction, a photon exchange. And there will be equation for this one that will be written in terms of a 5-point function. So it's an infinite number of equations, all coupled to each other, all non-perturbative. Now, what I was saying is that Dyson derived it from these perturbative series. But when you're making a series in perturbation theory, that means you believe that perturbation theory works. And perturbation theory can only work when the coupling is small. But these equations, in fact, can also be derived, which Schwinger did, from path integral formulation without any recourse to perturbation series. So your coupling can be as big or small, it doesn't matter, but you still will arrive at those equations. Some people call it Dyson-Schwinger equation. I call them Schwinger-Dyson equation because I look at the non-perturbative part that will derive by Schwinger. So that's also quite controversial. People even fight about it, which should be called Dyson-Schwinger or Schwinger-Dyson. But they commute, in my opinion. So, okay, so these equations, just to give them a bit more of importance, were first studied by a person who started the standard model of particle physics, Abdus Salam. He worked with his first student, Robert Dilbergo, in 1960s, and they wrote and studied Schwinger-Dyson equations for the electron, photon, vertex, and in fact, after Salam, Dilbergo continued to work on these equations for some time, for QCD as well. Sorry?
He ended up in Hobart.
Ended up in Hobart, yeah. In fact, I visited him and I stayed with him for 6 months and worked for him. I always wanted to work with Salam. I never had the chance to do it, but at least I wrote a few articles with Dilbergo. So that was good enough for me at the time. So he's still in Hobart. Actually.
Okay.
So he applied also on the standard model in QCD Dilbergo with a couple of other students, Keck and another student. Then in 1980s, Miransky and a lot of his group studied this problem, quantum electrodynamics. We know that this dynamical mass generation happens only in QCD, but he said, what happens if we were living in a world in which quantum electrodynamics would have a large coupling? What will happen then? And he came to the conclusion that even QED will dynamically generate masses for electrons if the coupling is above roughly 1. So you see that that's a value when you expect a field theory to become non-perturbative from perturbation theory. So when you start increasing your perturbation, even in QED, reach around 1, and you see that there is another solution, completely different, is generated, which is not seen in perturbation theory at all. So new solutions come, and that is what happens. You see, that was saying that you can sum all the perturbative series, but you will still not find that solution, which is non-perturbatively generated, because for that, you have to have alpha bigger than 1, such that perturbation series no longer makes any sense. They applied also later on in 1981 this problem to non-abelian gauge theories, QCD, and studied relationship between the first nonet of mesons, the mass relations between them. Then later on, Peter Maris, Peter Tandy, Craig Roberts, and others applied it to QCD, and there are many people who work on this. Effectively, what happens is, not going into the details, but still telling you that the devil is always in the details. And I will admit that you start with the Schwinger-Dyson equation for the quark propagator. It's linked to all infinite equations. You can't solve them non-perturbatively. Perturbation theory is the only systematic way of solving this. But you have to solve if you study non-perturbative QCD. So you do something which is non-systematic, but hope that you will capture some of the good things of that. So what they tried to do was make an ansatz for the kernel, which is there, which is for the product of the quark-gluon vertex and the gluon propagator as systematically as they could. I'll come back to it in a while, how that is done, and then solve these equations. And from that, you conclude that this is how your quark mass behaves. Now, there are a lot of things which go into this modeling. It's only a model. But what you have to try to make sure is that whatever model you give gives you the right mass for the pion and the right decay constant. And once you're able to do that, then a lot of things get fixed. That's usually enough to get the right physics, at least for the pseudoscalar mesons and vector mesons. Then life becomes a bit complicated. I'll try to rush up a bit things here. Then because just studying the quark and gluons is not enough, we have to make the bound states, and the bound state equation, relativistic bound state equation for two particles is the Bethe-Salpeter equation. So just as the quark propagator can be written in terms of two unknown functions, one is the mass function, another one is a different function because that's a spin-half particle. Pseudoscalar particles can be written in terms of four different basis vectors. You can't do more, you can't do less. P is the total momentum, K is the relative momentum between quarks. Okay, and that's all you can do. Then there are symmetries of QCD in the infrared. They're called axial vector identities. And once you have to try to see them, solve them, you see that in this equation for the Bethe-Salpeter, so this is a quark and an anti-quark inside the pion. It can have any kind of interaction like blobs that I was showing in the previous diagram. But it also carries the information of the quark propagator that we have already solved. So this kernel cannot be arbitrarily selected. It has to be selected in conjunction with the quark propagator equation so that you have the QCD symmetries obeyed and the infrared relationship which connect the quark propagator with the Bethe-Salpeter amplitude. So this is what I had already shown, what is called the mass function in the quark propagator, which starts with something like a constant value, goes down as 1 over p squareds, and it has also logarithms which come from QCD running coupling. So if this goes over 1 over p squared and you solve this, you find that these amplitudes which define your pion or kaon also more or less have similar kind of behavior and a certain power law, which follows the power law that comes from the quark mass function. Once you have this all, then I have only about 20 minutes left. So I think I have more things that I need. One of the things that you can study are the form factors. Right? But, pion and kaon, the fundamental bound states of only two particles, quark and anti-quark, but they are not stable particles. They decay very fast. You can't hold a pion, hit it, and see something, because when we hold it, it always decays to something else. So there are experiments which are done in a complicated way, and that also has its devilish details. So you, like in Jefferson lab experiment, you have an electron, it hits a proton, and you hope that in some of these experiments, this proton will go to a neutron, it will emit a pion, and that pion will serve as a source for this photon, and this photon will observe this pion. This should be almost on shell, and then you'll be able to study its form factor. It's a very difficult experiment, and I wouldn't go into the details of the experiment. I'll tell you what. Oops. Okay. So there is one more thing that comes into the study of this. Either you can study this kind of experiments in electron-proton scattering, and then you have experiments like Bell or like Babar or Bell, in which you have electron-positron collider. Also, BESS-3 in China is an electron-proton collider, in which sometimes it happens that it emits a photon. This also emits a photon, and it gives you a pi zero. In that case, what you study is what is called the transition form factor of two photons going into a pion. That also, these two photons can also probe the internal structure of this pion. But you see, in these kind of experiments, what is probing the pion is a photon. It's an electromagnetic probe. So what we also want to know is to understand what is the photon quark vertex. You may think it's not necessary, but we come to realize that it is necessary because it deals with the quark, which becomes non-perturbative, and it has all non-perturbative effects in this vertex. So although in terms of the Feynman diagram, gamma mu is the only thing represent an electron-photon vertex, but non-perturbatively, it can depend upon all these momenta, all these vectors, and then there are scalar functions, and you can make about 12 different combinations of this. And this is not only true of the quark-photon vertex, but also the quark-gluon vertex, which is the strong interaction vertex described by 12 different elements. So this is one of the hardest things you understand, because you have to truncate your equation, infinite number of equations, to a finite number. And if you make nonsense truncations, you'll get nonsense answers. So, and sorry, I did something nonsense, so let me go back. So what you do is that, I won't go into these details, you look at various kinds of identities that you have to fulfill, the Ward identities for the longitudinal part, the transverse Takahashi identities, LKF transformations, perturbation theory, renormalizability, God knows what. So you have to make sure that although you cannot do a systematic perturbative expansion, but all the necessary key features of a field theory are obeyed for photon quark vertex and also for the quark-gluon vertex. And then you can go on to do all these calculations. So, okay, let me just show like this. So you do this, and if you trust that I'm doing, honestly, my work, you can calculate the pion form factor. And this was one of the work that was done by one of the postdocs in our institute, who is now in Spain. This is the diagram that photon interacting with the quark inside a pion and gives you the pion form factor. You can also calculate the kaon form factor. And interestingly, what I see that, we know about the pion from 90 years ago, we still don't understand very well. And the problem is that an experiment gives you a result only for the pion form factor up till about 2.5 GeV squared. That's what experiment can do so far. And the theory can only tell you what the result is when Q squared goes to infinity. So the theoretical result we know somewhere here, and the experimental result, what we know is somewhere here. The true asymptotic QCD result. So where theory can tell us something, experiment can't reach, where experiment can reach, theory doesn't tell us anything. So this is a non-perturbative calculation that you can do. So this is our result at about 4 GeV squared for here and for the pion. This is with the kaon. And you can also calculate what is called the transition form factor, in which two photons go into a pion, but I probably will not go into a lot of details of that one. I want to go to some kind of a publicity thing, and also something that you guys probably know a little bit, going beyond the standard model. Anomalous magnetic moment of the muon is something extremely important. We want to study what are the limits of the standard model. A standard model will withstand the test of these precision studies or not. Okay? And so I don't have to go into detail. We knew that this G factor in the muon or electron-anomalous magnetic is half. Pauli knew it through Pauli-Schwinger equation. Then Dirac gave his equation in 1927 and 28, which implied that an electron had this G factor equal to 2, and therefore its magnetic moment was fit. Once the renormalization of QED was done by Tominaga, Schwinger, and Feynman, inspired by the 1947 work of Lamb, Schwinger was the one to do the first calculation of this at the first one-loop order. He calculated the muon or electromagnetic moment, anomalous magnetic moment, to be alpha over 2 pi. That is the deviation that you have from G equal to 2, and that is proportional to this Pauli form factor at Q squared equal to 0. Okay? So he calculated it to be alpha over 2 pi, which is 0.0116, 0.00116. But that was the simplest calculation. And now we want to see what happens if we make other radiative corrections to it. So there is a lot which can come. So what we can do, in what I have told you, is what I call the hadronic light by light scattering contributions that that come at order alpha cubed in QED level. You can see that this kind of diagram, which are correction to this Muon anomalous magnetic moment, can have these kinds of diagrams, and these kind of diagrams can come from one photon going to pi 0, another photon. That's where the transition form factor comes in, of two photons going to a pion, or these box time diagrams in which a photon is probing a pion, giving us electromagnetic form factor. So let's not go into the details of how all these calculations are done. You can use our techniques of form factors and eventually plug in and get your results. What I want to say to you is the following, that when you looked at this transition form factor, the pion going to two photons, we calculated this result, and we achieved this result to the same order of accuracy that lattice will give you or the dispersion theories will give you. So we were quite happy with that. In fact, there were some calculations which were not previously done by the people, the contribution of eta C and eta B pole, which are also pseudoscalar mesons, and that was the result that was computed by us. And you can see that our results are more or less at the same precision level that lattice and dispersion theory has. So, oops. Okay. So we can also do this. Okay, so I wanted to stop for a moment to tell you, I think I stopped at the wrong moment. It's not slides for me, it was from a speaker in Adelaide talking about the G-2, because some of you might be interested in what it is about. I don't work in detail, but I thought it might be of interest to you. There was a white paper written in 2020 in which we formed a part of it as well, some of the Mexican group. And there was a deviation shown from what the experiment tells us and what the standard model calculations theoretically tells us, that there was a difference about 4.22 sigma. Then later the same year, when this white paper was out, there was a lattice calculation telling that no, if you make the results a bit more precise, the result should be closer from the calculation to the experimental result. And in fact, this result, if you just believe in this result, the difference from the experimental value is only 1.5. Then that calculation has been repeated by the same group, and now this is more precise, and the direct difference with the experimental value, if you believe in them, it's only 0.9 sigma. They are not the only ones. There are other people telling us that if you make the lattice calculation more precise, we get closer to the standard model instead of going further from this. So I thought that that might be of interest for you to know. The major contribution that comes, of course, is from QED. But the major contribution to this observable, where the errors come from, is QCD. It's the vacuum polarization diagram or the hadron light by light diagram that I have calculated. So unless you reduce these errors, we can't go any far. So there is, still lattice results which some claim that it is far and some not. So this is the connection. But my connection of working with pion form factor was not entirely for this thing, although we checked these results. For me, it is that pion and kaon, the simplest bound states of QCD, and we want to understand how that structure forms. So that is important. In USA, every 7 years, there is a long-range plan. In 2015, it was told that it's an important thing to calculate. So I was telling you that the experiment only tells us for small values of Q squared, and theory tells you for large Q squared. So very soon, not very soon, 10 to 15 years from now, we hope that through an upgrade of Jefferson lab, double upgrades, and Electron-Ion Collider should be able to measure this form factor till the values that asymptotic QCD can predict. And our theoretical tools will be able to trace out all the region of increasing Q squared. And that would be the first time we'll be observing something that ranges from the perturbative aspects of QCD to the non-perturbative aspects of QCD. And both theory and experiment should be able to see if that can be done or not. So there is a 12 GeV upgrade, which has already been done of Jefferson Lab, that will be measuring the pion form factor from 6 to 8 GeV squared. And so those measurements will go up till here, and these are the error bars that they will be measuring. So far, we only have about 3 GeV squared, and also the pion will be measured till about 5 GeV squared. And then there is a proposal which came only about a year ago in this workshop and a little before that there is a next upgrade of JLab up to 22 GeV that has been proposed, and that should be able to measure pion form factor till 15 GeV squared and the kaon form factor till 10 GeV squared. And I'll tell you what will be the importance of that. And that means that not only up to 7.5 in the next upgrade, which will hopefully be funded by DOE, would give us a result at about 15 GeV squared. And then the final thing will come with Electron-Ion Collider. That should be able to make the pion form factor till 40 GeV squared and the kaon form factor till 20 GeV squared. And in their yellow report, this is saying that it's an important thing. The phenomena of emergent mass should be explained by understanding these form factors. And of course, then we should be able to go much higher in observing it. And therefore, what we need is a computation for that. And I think I'm almost running out of time. So I'll probably, maybe this is the only transparency that I can, sorry, the only slide that I can show you. Will probably not like calling it a transparency. So, so I use what I call the Schwinger-Dyson equations. So I have to tell you that there are extremely good things of it associated with, and there are extremely ugly things associated with it. The good thing is these are exact equations of QCD and QED, but you can't solve them exactly. Okay, that's the bad thing. Also, the good thing is because they don't depend upon how big or small the coupling is. Within the same formalism, you can study the perturbative and non-perturbative aspects of QCD. So that's the beautiful part. But in close analogy with QCD, you can only solve it for some very simple system. And pion or kaons are those systems that you can study. So if you have to study simple system, you can do a very sophisticated study. When you're studying baryons, it gets very ugly. So you make approximation which almost ruin the Schwinger-Dyson equations, and you can only give certain observables correctly, only the static ones which don't run with momenta, just like the masses of proton and neutron at excited states, but nothing more interesting than that. So recently, our group has been doing something intermediate, what I call forming algebraic model, which will have somehow mimic the correct power laws of QCD, even if we don't have the correct logarithms, but at the same time trying to maintain some of the simplicity of these ugly models. So try to have something good, simple, but still as accurate as we can get other than the logarithm, at least to get the power laws right, okay, for large Q squared. So I would not go into defining this model that one of our postdocs gave about the quark propagator and the beta salpeter amplitude. We don't solve it now. We have already solved it. So we model it with something. And once we do it, then eventually we can do all the things. With this model, you can calculate the generalized pattern distribution functions. And then we can project it to calculate the pattern distribution of Feynman for the pion and kaon. And you can integrate out this, and you can also calculate what is the pion kaon form factor. And because there is a model and it's simple, we can not only calculate it for low values of Q squared, but also large values of Q squared. And I would skip all these details, and I'll just give you what we eventually get. I'm just trying to tell you here that when we are for small values of Q squared, we can do a sophisticated truncation of QCD. And then in that region, we can try to see how good our model is doing or not. And our model has this, I have no idea what it's this band, this pink band. No, it's a blue band. It's a blue band, but it's not seen here because it's hidden with the exact results that we have. And this blue band also, it does quite well, along with the more exact calculation that we did. But because it's a simple model, we can extend it to much larger values of Q squared. That I was showing is the expected range that we have for 12 GeV upgrade of JLab. 22 GeV upgrade of JLab, and the EIC. Okay. So we have been able to measure, to calculate the form factor up to these 40 GeV squared, where the experiment will be. So we have a prediction. You can always have a wrong and right prediction. The experiment will tell us how good or not it is. So this is some earlier calculation of Schwinger-Dyson equation. This red curve, ours, has some bar of uncertainty depending upon the uncertainty of actually the observables that there are. Pion mass, pion decay constant, and pion charge radius are not accurately known. So if we input that uncertainty, that magnifies for large Q squared, and that's what comes in. This is a recent calculation of Brookhaven National Laboratory lattice QCD group. It actually came out also about a month ago, just when our paper was published. So that's more or less the prediction. This maximum comes out to be about the same value, where you will have the logarithmic corrections coming a bit more dominant in QCD, but that's a bit debatable. So we have managed to do it. We also have the results for the kaon. At the moment, in the 12 GeV upgrade, people are evaluating up till 5.5 GeV squared. The pion form factor, these are the projected results they have for the Jefferson lab. It will be known in about 1 year's time. So we also have the prediction for that. This is again our band, and that's the lattice result that has been in also about a month ago. It's not doing so. So the idea is that we have provided these predictions, which should be measured, agreed upon, or refuted in future experiments. So that's where basically I will stop all the things that I have done. What I would like probably is to mention to you that there are some other things which can be done with these models and things, like measuring this form factor in the time-like region, not in the space-like region, to understand the resonances that come from hadron physics. This is one of the first works that have been done in this field by Angel Miramontes. And eventually, one of the things that we want to do is not only pion and kaon, but proton and neutron, and their excited states, and the excited states of pion and kaon, because only these transition to the excited states and understanding 2 and 3 party particles that we can really understand. If we can explain it with one single formalism, all of these, we can have some hope of understanding QCD, and especially a transition of QCD from non-perturbative to perturbative phenomena, from confinement and chiral symmetry breaking to what we see in perturbation theory, from this solution to that solution. I have not mentioned anything about confinement here, but these propagators are very interesting. When you have perturbative propagator, they are simple Feynman propagators that you know, but when we calculate them non-perturbatively, you see that you have to calculate not only on the real axis, but also on the complex plane. And when you go into the complex plane, they have very peculiar behaviors, and some of that might be associated with confinement, but that's a bit unexplored region. We hope that we can all cover this in next 100 years. Well, hopefully that's. Thank you very much. That's where I stop.
Thank you very much. Questions? Room or online? So maybe I'll go first. So just a very naive question. So the form factors that you showed for pion and kaon at very low values of Q squared, the match between the theory and experiment is sort of so good that you cannot even tell the difference on the plot. Yes. Is there any discrepancy there? Is it you think that at low values of Q squared everything is pretty much understood perfectly?
That's where you go to something like infrared QCD things, and the thing is that you know that whenever you model your lattice or Schwinger-Dyson, even when you should lattice study, you have to give what is the pion mass, for example, and then you compute everything else from there. So most of the things you have to fix some infrared parameter. And once you do the infrared parameter fix, then closer to that region, usually your results agree. So that's one of the reasons that in that region, you have the correct slope. You know what the charge radius is very accurately. Any modeling will generally fix the charge radius, fix the pion mass, and automatically the decay constant, decay constant of the pion gets fixed. And for some Q-square, you expect that your results will be pretty accurate. And then the deviation will start coming as you go further away from Q-square. So that's like any modeling which will take into account some experimental observation. What you hope is that that will continue that agreement for larger and larger values of Q-square, and then you don't have to do any other twitching or changing of the parameters and things like that. What we know is in the largest Q-square region, when it is above any other mass scale, your photon probing momentum scale, you have the result known by Brodsky and Lepage in early 1980s calculation, and that should be reduced. At the moment, there is no sign of going towards that because when you go higher up, for example, if you have this, the asymptotic QCD results lie somewhere there, and at the moment, experiment is going higher up. So it will have to go up here, and if asymptotic QCD is to correct, it's turn down and go somewhere there. So that's the ideal thing to happen, is that the asymptotic QCD predictions, which we think are exact, should be approached at some large value of Q-square. We can't say which one. It just tells us that it should be larger than any other momentum scale squared that is involved. How much is it? The theory doesn't tell us.
Could you talk a little bit more about how this interfaces with the lattice approach? Like you mentioned lattice in the context of the G-2, the muon. Are there any other agreements with these different theoretical approaches elsewhere in the literature that maybe we're not aware of?
The differences between, yes. For example, one of the differences that can be, the thing is I told you that when people apply these methods to baryons, use the same effective quark masses and the same mechanisms, lattice has sometimes a different view. Some of the state comes as dynamically generated states. Schwinger-Dyson equations give them a different interpretation. Sometimes they talk about parity doubling and saying that, oh, well, when you go to higher excited states or higher masses, there seem to be parity doubling. That is, the two opposite parity states have the same mass. Here we say that they should have a mass difference. But people who do this continuum QCD then, well, what you're saying is parity doublet is accidental parity doubling. It's not that they are, parity partners. This may have another parity partner, or this may have another parity partner. Especially in the baryon region, there is a difference. Lattice sometimes even gives you an inverse ordering of masses of Roper and 1535. Roper comes out to be higher in mass than 1535, and it should be the other way around. So there are differences. The good thing is that the lattice QCD makes less assumption. The bad thing is that when up and down quarks are involved, you have to go towards the chiral limit, and the chiral limit is very hard to take for QCD. That's why, for example, the pion form factor is only known in a certain region with a big bars, because taking the massless limit is not easy. So sometimes it is complementary. What these studies can tell us that for us, for Schwinger-Dyson equation people, the chiral limit is easy to take. Heavier things are more difficult. So it's complementary in various ways. For example, the very first graph that I showed you, which is produced by this Schwinger-Dyson equation people of the running coupling of QCD going to infrared and saying that it flattens out in low region of Q square, but then there is also an error bar showing. Oops, it's hard to go like this. I'll probably still keep going. I think I'm almost reaching there. Okay, this one. So this error band and calculation of alpha q square come from Schwinger-Dyson equation studies, but they use the result which is calculated by lattice QCD for the gluon and ghost propagators, and the errors come from there. So there's something one scheme doesn't know and makes use of the other one, and of course there are some issues. Like there are a lot, there are lots of approximations that have to be used to build a model for SDE studies. You have to be just aware of what the errors can be generated from those modeling. Lattice QCD is more exact, but can do a bit less at the moment.
And the plot on the left-hand side, that's from the Schwinger-Dyson equation.
That comes from the Schwinger-Dyson equation.
But the individual quark mass on the right, is that come from lattice or?
Oh, these ones?
Yeah.
This is actually when you do the how do you say? When you have the propagator, that depends also on the renormalization scale. So at some scale, you have to match with the scales of the real quark masses that you know, and that comes from there. The only thing is that all this study from Schwinger-Dyson equation is for Landau gauge QCD. Okay, we haven't been able to do for other gauges to see how it works. So for example, the propagators all are expected to be gauge dependent functions. Even this mass function would depend upon the variation of gauge. It will not remain the same. So in fact, the view of the masses of quarks running Q squared is not, it can depend upon the gauge. The only thing we are recently working on that it doesn't matter which gauge you are and whether your green functions depend upon the gauge, the physical observables still come out to be gauge independent. So there might be small variation of this. So that's not really as much telling you, oh, this is the physical mass of the quark. It's not, okay? But anyway, the quark mass function can't be real. Even quarks are not real. You just only see them indirectly. So to expect that we know exactly how its mass is traced is not correct. It's not. It's a rough picture. But the physical observables are gated.
Did you say that the JLab 12 results are a year away or something?
For the kaon form factor, yes.
How long are you having to wait for the JLab 22 and the EIC?
EIC timescale would be about 15 years from now. And the JLab 22 GeV may be a fairy tale. What I'm saying is that depends upon if it's funded or not by the government.
So that might depend on the JLab 12 results, perhaps.
It will depend upon that. Yes, pion result will be coming in 2 years' time, they told me. Kaon result is coming earlier in 1 year time. But then the thing is that EIC and JLab a lot of things will be done. The same observables they will be calculating, but EIC will be calculating it much more accurately. And then when their funding demands will go, it's likely that they won't be able to fund both the projects same time. So it might be that one wins over the other. Or if the money is divided, then both programs may be delayed because it will be divided. So don't really know how it will work out. 22G upgrade, it's only a proposal and it hasn't yet been approved.
All right, last chance for people online. See any hands? So yeah, let's thank you very much.